You are given that f of x is equal to x plus 3 times x minus 2 times x minus 5. Part I, sketch the curve y equals f of x. So the x plus 3 is telling me that there's going to be a root at minus 3. The x minus 2 is telling me there's going to be a root at plus 2. And then the x minus 5 is telling me there's going to be a root at plus 5. If I were to expand all of this out, I'd have a positive x cubed. So I know it's going to start by coming up here like this. It's then going to come back down through 2. And then back up through 5. The other point that I want to mark on here is the y-intercept. What's this coordinate here? I can find that by making x 0. So if I substituted 0 in here, here, and here, I'll get 3 times minus 2 times minus 5, which is 30. So there we go. I have sketched f of x. Part II, show that f of x can be written in that form. So I'm going to expand these brackets. So let's leave the x plus 3 for now, and let's expand out the x minus 2 times x minus 5, which will give x squared minus 5x minus 2x plus 10, which will simplify. We can collect up the minus 5x and the minus 2x to be minus 7x. Now multiplying everything by the x, we'll get x cubed minus 7x squared plus 10x. And now multiplying everything by the 3, we'll get 3x squared minus 21x plus 30. Collecting the like terms together then does give us the form that we needed. Part III. Describe fully the transformation that maps the graph of f of x onto the graph of y of g of x, where g of x is equal to x cubed minus 4x squared minus 11x minus 6. So let's take my f of x that I've just written down, and let's write g of x underneath it so we can compare. So the g of x was x cubed minus 4x squared minus 11x minus 6. So notice that all of the terms involving x's are identical. The only difference is the y-intercept on the end here is 36 less. So we have subtracted 36 from all of the y coordinates. Therefore, this is a translation by the vector 0, because the x coordinates haven't changed at all, and minus 36, because we've subtracted 36 from all the y coordinates. And then part 4, or IV, we need to show that g of minus 1 is equal to 0. So let's do that. Let's substitute minus 1 into the g function. So we'll get minus 1 cubed minus 4 times minus 1 squared minus 11 times minus 1 minus 6, which gives minus 1 minus 4 plus 11 minus 6, which does in fact equal 0. So I have shown that g of minus 1 is equal to 0. And what that's telling me is that x plus 1 is going to be a factor. So we can do a little bit of algebraic division now then, which is why I'm just going to give myself a little bit more space. So let's take our g of x function and let's divide that by x plus 1. Like I say, if I substitute minus 1 in and get 0, then that's telling me that x plus 1 is a factor. X into the x cubed goes x squared times. X squared times x is x squared. X times squared times 1 is x squared. And we'll take that away. X cubed, take away x cubed is 0. The minus 4x squared, take away x squared is minus 5x squared. The x into the minus 5x squared goes minus 5x times. Minus 5x times x is minus 5x squared. Minus 5x times 1 is minus 5x, and we'll take that away. The x squared terms will cancel out. The minus 11x minus 5x will be a plus 5x. So minus 11x plus 5x is minus 6x. The x goes into the minus 6x minus 6 times, and multiplying that out leaves us with 0, which was what we expected. So we can now say that g of x is equal to our linear factor of x plus 1 multiplied by the quadratic factor, which is x squared minus 5x minus 6, which can then be factorised a little bit more into x minus 6 times x plus 1. And we can now see that x plus 1 is a repeated root. And therefore, this is my final answer of writing g of x in its completely factorised form.